Welcome to today's video. I'm Andreas Hanuja and I love Mesh. This is the third video of our MeshMas behind the scenes series. If you missed the previous videos where we learned the basics of creating interactions in Microsoft Mesh, check out our I Love Mesh community. In this series we explain the technical background of our MeshMas experience, beginning with easy minigames and concluding with the most advanced gamification elements. Today we look at the Snowperson building system. We will go into less detail than in the last videos, but nevertheless I will try to take you all with me. If you want to rebuild the system, pause the video in between and feel free to ask any questions in our I Love Mesh community. First, let's briefly answer why we have such an application in MeshMas in the first place. Building physics-based Snowpersons is intuitive, fun and inspiring. In contrast to scripted interactions, physics-based interactions allow you to be creative and create replay value. They often need less effort to implement and provide more value to the customer. Let us first check out which features we try to achieve. Our system allows us to roll snowballs over the ground to increase their size. Then we can build a snow person out of the snowballs. The snowballs are sticking to each other. We can also grab some accessories and stick them to the snow person. Our last feature is that we can melt snowballs again if we have grown them too much. Okay, so now let us check how our Unity hierarchy looks like. So first we have our snowballs, each containing a rigid body and a mesh interactable setup component, which you already know. What is new is our sticky body component. This allows physics-based objects to stick to other objects. In this case we want to restrict our snowball to stick only to the ground. Sticky body components can for example be restricted by target object names. Here our ground object has a special name. After the snowballs we have our accessories, each with a mesh interactable setup component, rigid body component and a sticky body component. For the colliders we are careful here because mesh colliders can get expensive quickly. We approximate shapes with box colliders here. Lastly, we have two trigger volumes, the fire zone and the snow zone, which we're going to refer in our visual script. Before we start, it makes sense to quickly think about how we want to achieve synchronization. In this scenario, our client can do multiple local interactions like growing the snowball or shrinking it. The visual interaction is already seeable by other clients because the rigid bodies are synchronized. From the programming side speaking, the only thing that changes is the radius of our snowball. If we just share this one variable and apply the effect on all clients, everything is synchronized already. So let's dive in the already open script graph. Don't be afraid, I explain everything step by step. This bottom part is about the radius variable we just mentioned in the drawboard. Whenever it changes or on application start, we calculate this crazy radius function. This function utilizes some variables for a nice mapping between radius and our properties. Such variables allow tweaking in runtime for getting a mapping curve that just feels perfect. If you want to copy this approach, just feel free to pause the video and copy my values. One important thing is our min size variable. Our function is returning values in a range between 0 and our variable n. Without adding a fixed min size to the function, our snowball would disappear at the minimal radius. The output of the function is utilized by these two branches. First, it is used to calculate the mass of the snowball, which we then later set to our rigid body for realistic feel of the physics. Second, we apply it uniformly to the scale by multiplying it with vector 3.1. Now we have ensured that all clients have the correct snowball properties whenever the radius variable is changed. Let us continue with the change logic. This logic is based on two trigger zones, which we already mentioned in our hierarchy. First, when entering a trigger that contains the tag snow zone in its object name, we set the local graph variable that we need for our further calculations. On trigger's day, we handle the update logic. As this gets expensive quickly, try to filter out as many calls as possible. With our if condition we can already rule out all snowballs immediately that are not owned by the local client. Then we check if we are in the fire zone for melting the snowball or if we are in the snow zone for growing the snowball. In the melting case, we calculate the behavior based on a melting speed variable. Multiplying with fixed delta time is not such important as the physics tick rate is usually constant. Nevertheless, this avoids issues in case of differences between our build and editor simulation. With the maximum node, we make sure to avoid shrinking our radius below 0. Finally, we update the radius, which will be synchronized automatically between all clients and applies all the property updates on our snowball. For growing, we first calculate the movement of our snowball by subtracting our local variable last pos from the current position. We also include a variable for a minimal movement threshold. This calculation then finally determines how much we want the snowball to grow. After applying the radius, we should not forget to update our local variable for the next script execution. This was maybe a bit overwhelming, but don't be afraid, we check the overall program flow again in a second. When selecting an object in hierarchy that contains a visual script, the current instance is previewed in our graph window. You see right now how our logic is triggered each physics update, while the guard clause filters out all the calls. When we now grab the snowball, our bottom branch is executed as the snowball is right now in the snow trigger zone. If we move the snowball outside the zones, the logic is no more executed because the on-trigger stay event is no more triggered. By moving the snowball to the fire zone, you can observe how the upper branch is executed, which handles the melting logic. Let us observe our logic in action. Whenever the radius is changed, our bottom part of the script is updating the mass and also the scale, which we can observe immediately. Now let us finish the video by playing a little bit and building a small, minimalistic snow person. Thank you for your attention. This concludes our today's video. Stay tuned for the next video where we show you how we made even Santa curious about our MeshMas environment.